You're listening to The Uncommon Engineer. I'm your host, Steve McLaughlin, Dean of the college.
We're just absolutely pleased as punk to have you with us. Please say a few words.
So Georgia Tech is kind of a mini NASA.
So we're going to find a pressure ahead to do the CDH burn. It doesn't look like this is going to hurt anything.
Now pressurizing, and we're coming up on the power transfer. Stafford making a final check of his computer. 10, 9. We have ignition sequence start. Engines on. 5, 4, 3, 2. All engines running. Launch command. Liftoff. We have liftoff. 49 minutes past the hour.
Man set foot on the moon in 1969, and since then, we've been reaching ever deeper into our solar system. We're discovering evidence of water on Mars. We step beyond our stellar neighborhood with Voyager 1, the only Earth object to reach interstellar space. And now, yes, we're exploring commercialized space travel.
Looking great here. You're looking beautiful.
Welcome to The Uncommon Engineer. Conversations about the impact Georgia Tech engineers are having on people and society, and maybe in ways that you don't expect. I'm Steve McLaughlin, Dean of the Georgia Tech College of Engineering. Today, we're here to talk to Professor Brian Gunter from the Georgia Tech Guggenheim School of Aerospace Engineering. Brian Gunter, welcome to The Uncommon Engineer.
Thank you for having me.
Flight crew, OTC, close and lock your visors, initiate O2 flow.
Roger, Hawaii, reading you loud and clear also.
You know, we hear lots in the news about space missions and launches, whether it's the space shuttle. You know, Elon Musk is certainly in the news a lot around SpaceX, and I understand you're involved with SpaceX on a project. Can you talk about that?
That's right. We have in development at Georgia Tech a small satellite mission. It's called the Ranging and Nano Satellite Guidance Experiment. And I'll get into some of the details in a second, but it is a small satellite. Think of a satellite that's maybe the size of a large coffee cup, and there are two of these together. So together they're about the size of a loaf of bread. They will be launching on a Falcon 9 rocket, which is made by SpaceX, and that should be launching in the fall of 2018. The specifics are, you have to be very flexible when you launch satellites because the dates always change. The range mission is, think of these two small satellites, and the goal of the mission is all about getting precise, absolute, and relative positioning. So most small satellites only know their position in space to tens of meters, and we want to get that down to centimeters. So we want to know where these satellites are at any point in time down to centimeters. And in addition, we want to know, because there are two of them, they're flying together in this sort of leader-follower formation. We want to know how close they are with respect to each other down to millimeters. And so we have all this instrumentation. We have a laser rangefinder on there. We have a miniaturized atomic clock, which we think is the first one that will fly in space. We're also testing various secondary experiments. A lot of the operation of the satellites are going to be autonomous. So they're so small, we only contact them maybe 5 or 10 minutes a day. So the rest of the day, they have to work on their own. And to maintain their formation, let's say we want them fixed at 10 kilometers apart, they have to do a lot of that themselves. And so there's a lot of interesting development that goes on with that. And there's no propulsion systems on these small satellites. So they have to do what's called differential drag, where even though you're in space, there is a small amount of atmosphere, and you're going 7 kilometers per second. So you're really moving fast. So even the smallest bit of atmosphere is still interesting or still can create a force on the satellite. So what we do is we'll turn the satellites and give it a little bit different area that is heading into the drag forces. So because of that, then we can stretch things back and forth.
So you have students in your lab that are making these satellites and interacting with SpaceX. What's it like to interact with SpaceX? You mentioned you got to be patient.
So the mission itself was accepted as part of, we got the launch, we had to build the satellite, but we got the launch awarded to us through a proposal, through what was at the time the Skybox CubeSat partnership. So Skybox was a company. It's now owned by a company called Planet. And for those who maybe follow satellite remote sensing, Planet is now a company who has a number of orbiting imaging satellites that are constantly taking high-resolution images of the Earth. So we got the launch through them, and they awarded us a launch on one of their following satellites because they have larger satellites, and we go along on what's called a rideshare. Primary customer and then our small university satellite go wherever there's space on the rocket if
I
there's
see.
extra mass.
Okay.
And so the way that SpaceX came into be is originally we were supposed to launch on an orbital ATK rocket. And so it was going to be Skybox, now Planet, that was going to pay for the primary rocket, and we were going to be a rideshare on that. Then, as we've learned, a number of launch delays because you're waiting on the primary customer. So you don't have any choice on when and how you go up. And so things changed. So things were rescheduled, plans changed, and so we moved from an orbital ATK launch to now this launch that's called the spaceflight SSOA, or what they're calling the Small Sat Express, that is going up on this Falcon 9, and that's a dedicated mission that's operated by a company called Spaceflight Incorporated. So the way it works is we interact with what's called a launch service provider, and Spaceflight is that company, and then they interact with the SpaceX, the rocket provider.
So you talked a little bit about the fact that you're going to launch these 2 satellites, and the goal is to run some experiments that help finally control position or where they're located down to a small scale. Do I have that right as the goal or purpose?
That's correct. So the primary mission of the mission is this relative and absolute positioning. So we want to find out how to control or how to know where the position of these small satellites are to a level that has never been done before for these small satellites. So that in itself is an enabling technology. It's one of these characteristics about a satellite system that if you know that, then you can enable a number of different other mission concepts. So think of very tightly controlled formations, think of constellations, or think of, like we talked about earlier, where you have coordinated measurements, and you need to know precisely where things are so that you can take, whether it's images or whether it's ranging data, in a very coordinated and precise manner. And so sometimes you need to know that level down to centimeters. The secondary part of these missions, that many of these CubeSats are technology demonstration missions. So you are testing out whether new components are going to function in space, whether they do what you think they do. So we have several, like I mentioned. One was a miniaturized atomic clock. Another is a laser ranging system, and this laser ranging system also caught the attention of the Navy. So we had a follow-on grant from the Office of Naval Research, and what we're doing with this is for the same laser that we're using to do intersatellite ranging. So think of a rangefinder that you might get at a hardware store or something like that, except now we're pulsing this over many hundreds of kilometers possibly. That same laser can be used, if you think about it, pulsing it on and off can be zeros and ones. So it has essentially doubles as a laser communication system. And that's what the Navy was interested in. So we're also demonstrating what we hope to be the first intersatellite or cross-link laser communication system. That'll be a very low rate. It's not going to break any speed records, but it will demonstrate the links, it'll demonstrate the technology, whether these small components that you could just literally hold in your hand, could they service as a laser communication system.
So you're living proof of, when NASA goes to Congress every year to kind of justify that, hey, what we're doing in space matters. It's not just the mission, but it's the things that you learn along the way. And sounds like you're testing a number of those enabling technologies that even separate from your, the project per se. You're demonstrating new things to even solve your mission. And you're living proof of why we need to support NASA.
11 Houston, if you could comply, we'd like to see some smiling faces up there. Okay, we'll reconfigure the TV for that. Roger.
Where do you think manned space flight is headed? You keep hearing about possible manned missions to Mars, but what about some of the other planets? Where do you see, looking into your crystal ball for not just 20 years, but 100 years, where's man headed?
Well, I think in the near term, most missions are going to be robotic. The reason why is the space environment is extremely harsh. So we know this. It has extremes in temperatures. There's radiation. And, of course, there's not this breathable atmosphere or food sources readily available. So you have to build spacecraft that bring all of that along with you to protect the astronauts or the humans that are on the trip, plus bring all of the food and water and air that they need for the journey, not just there, but also coming back as well. So it becomes very expensive. So just to give an example, if you go to the SpaceX website, since we're talking about SpaceX, the Falcon Heavy, which is this next generation of a very heavy lift rocket vehicle, it can carry, according to their website, 37,000 pounds to Mars. And if you think about what a mission would cost, a manned mission anywhere, Mars, even to the moon. You could think of billions of dollars. To put it in perspective, the Cassini mission, which was wonderfully successful and just finished up its operations, that was around $3.3 billion for its mission.
Yeah.
So you would expect it would be at least as complex and expensive as the Cassini mission if you're sending humans. And at just 37,000 pounds, when you do the math, at say a $4 billion mission cost, you're talking about spending roughly anywhere from $50,000 to $100,000 per pound of mass. So it gets really expensive. In addition, there's some very other sort of physiological and psychological challenges that go with manned spaceflight that maybe a lot of people don't know. The human body isn't meant to exist for long periods in zero gravity. We're meant to be here on Earth. So there's problems with bone densities, muscle mass. There's also been documented cases with problems with eye pressure causing permanent eye damage. There are interrupted sleep cycles because you're not on this Earth cycle of day and night. And so it's very, there are certain things that have to be overcome before we send somebody off. And a round-trip mission to Mars, you can expect to be maybe 3 years going there and back. And there's also some psychological challenges. You're basically in a solitary confinement for 3 years as an individual, and that's very difficult to overcome. When they screen people to be astronauts, their psychological makeup is just as important as what their technical skills might be. So that said, I think the challenges for human exploration are not insurmountable, and I believe the technology is there to do that or can be developed in the near term to put humans on Mars or other celestial bodies. We don't have to go to Mars. We could go to asteroids and comets. And these are also been proposed. And sometimes they're a lot easier because if you go to Mars, you go to a very large planet that has a large gravity that you then have to overcome on the return flight. But if you were to land on an asteroid that there is no large gravity, getting off of it is much easier.
I see.
But I think it just needs the investment and the support behind it. So I think we can do it. It's just very expensive.
Missions to other planets. What are the other kinds of things that you see out there, either that you're working on or that Georgia Tech's working on, or things that maybe our listeners haven't heard about?
Well, I would say since we're talking about manned and robotic missions, I would also argue that there are still a tremendous amount of things that robotic missions can do, and some of them that they should be doing instead of humans. So not everything is something that we should do with manned exploration. And one of them, for example, is, let's say, an orbiting imager, like we've talked about, that you're just gathering real-time information that's up there for decades at a time, gathering 24/7 data, 365 days a year. That information is best done by robotic missions. And so sort of the link to that is some of the work that maybe is not so known, where we use remote sensing. So I build satellites, and we have this whole CubeSat and small satellite program. But another aspect of what I do is actually using the data from those missions. And because they're launched for a reason. And a couple of good examples are some NASA missions that I've been involved with in the past, the GRACE mission and the ISAT mission. GRACE was a mission that was designed to observe the time variable gravity of the Earth. And that's important because anything that moves on the surface of the Earth, water, snow, ice, oceans, it's all mass, and mass and gravity are linked. So when you observe the time variable nature of Earth, the time variability of it, you are also understanding what are the processes that are causing that change in the gravity. And so we use that remote sensing data from these NASA missions to observe all sorts of things that people may not know about. One of them is I study the motion or the ice mass and solid Earth changes in Antarctica. And you may ask, why are we interested in the changes in ice and the solid Earth in Antarctica? And the answer is that it has a direct influence on the rest of the world in terms of sea level change, because it's like a cup. And Antarctica is, if you were to put a ping pong ball in a glass of water and you push it down, the water would rise. Pull it up and it would lower. And Antarctica is a very large continent. It has 70% of the world's fresh water on it. And so observing the changes in Antarctica directly influence our understanding of the water cycle, sea level change, climate change, all of this. So we've been using that data, and for time variable gravity, we can use it to observe. And gravity is an interesting observation because it's not limited by a camera. Like a camera is limited by its line of vision. So if it's something underneath a tree, you're not necessarily going to see it, but gravity is insensitive to that. So we can observe changes in underground aquifers. So we can monitor, let's say, the behavior of large river basins or large aquifers that we depend on for agriculture, for food production. And so this type of remote sensing data, looking at the data that comes from these major NASA missions, is also another one of our major objectives. And I'll also say that the ICESat and GRACE missions that I've been working with, they have now follow-on missions. So GRACE follow-on just launched a few months ago, or a couple of months ago, in early 2018, and ICESat-2 is set to launch later in this fall in 2018. So these two missions will continue to not just look at Antarctica, but do global mapping and global, and ICESat I didn't mention, but it measures the topography. It's using LiDAR systems to measure the changes in the surface and the volume of the Earth, and the GRACE mission measures the change in mass. So these are fundamental properties that we are observing and will continue to observe now for many, many years to come. But that's something that I'd like to throw out too, is that we're not, or at least I'm not, just focused on just the hardware and just the satellite components, but I'm also very much interested in what the satellites do and interpreting the data that they generate. So, in all the things that you talked about, your expertise, your interests, span a huge range of things. And what I'm really curious is, your path to becoming an aerospace engineer. And, even as a kid, or whether it's in high school or college, can you talk about how you found your way to doing all of these interesting things? I think there's so many young people that might be out there trying to understand. They've done a pretty good job, I think, of saying what engineers do, but how did you find your way there? Well, I've always been sort of interested in designing things. So as an engineer, your job is to build something to complete a particular task. And that's a very big umbrella. And so my particular task is the exploration of space. You're built with basically taking a problem that needs a solution, and you build something to either solve that problem, and that can also encompass programming and coding and analysis. And so I've always sort of drawn to that. You have some sort of unknown problem that you'd like to fix, and you know that there's a technology that maybe if you just design it right could solve that problem. And that's always appealing to me. And then there's an additional appeal to space, because there's just so much we don't know about space. We don't know about working in the space environment or the origins of life, and even every new mission that NASA sends out, especially the planetary ones, comes back with this host of just amazing images and new insights about things. And so that's also a very big draw, that you have the opportunity to start, I guess, tackling and answering some of these big unknown questions. So that was a big draw for me. And how I got into specifically this particular field, it started, of course, with graduate school, undergraduate and graduate. I started first as a mechanical engineer, and then I transitioned into aerospace engineering because of this appeal to work with space. But initially, I thought, I was going to work as a mission control guy at Johnson Space Center. That was what most people's, I think, vision. You're either going to be an astronaut or you're going to work at mission control, because you see this in popular media and movies and things like that. And the reality is, when you get into it, and I started working with the original GRACE mission when I was at University of Texas at Austin. So my advisor was the PI on the GRACE mission. And I got this other insight into, wow, there's this whole science aspect to the engineering that we do. So the science and the engineering was a really big appeal for me. And so that's what I continued doing. So I started blending more and more the remote sensing and the science and the engineering. And the more I understood more about the purpose of these missions, the more I enjoyed that. But I also wanted to also bring my engineering knowledge to say, aha, I think we could do this, or I think we could do this, or if we analyze the data this way, we'll get into some new insights. And so it's just sort of fed on that. And I've built that over the years, and I was able to bring that to Georgia Tech, but now realize it a little bit different way with all of these small satellite missions that we have in development.
You kind of touched on it. Did you think you wanted to be an astronaut at one point?
I did. There was a time, and I did apply to several rounds of the astronaut program. It's extremely challenging. You've got 20,000 people applying for 6 positions, of which 3 will go to civilians. So if I wasn't an Air Force pilot or a Navy pilot. And so it's extremely competitive. But ultimately, I tried, but I wasn't disappointed, of course, because there's so many other things, there's so many other contributions you can make.
Yeah.
And who knows, depending on how things go with some of these new ventures with space tourism, maybe before my life, I'll still be in space.
Yeah, that would be. Is that something you think you'd like to do? If right now it seems to be for billionaires.
I'm going to hold out to make sure that I worry less. Well, the money is a factor because I don't have $10 million to do some of these really specialized trips, but I would like to wait for just to make sure that it's demonstrated to be safe and make sure that these are reliably and before you trust your life strapping yourself onto a rocket and orbiting Earth, you want to make sure that it's going to be a safe experience.
And do you think in the next 20, 30 years, do you think that'll be a possibility?
I think you'll see it won't be I think something that you just book up online, it won't be that popular. But I do think that in the next 20 years, you're going to see at least suborbital flights. Maybe you just get weightlessness for an hour and a half or 2 hours. Yeah. Possibly even full orbits where you're actually orbiting for maybe some days and then you return. Mm-hmm. I think that there are certainly companies who are pushing very hard to achieve that. And I would very much like to do that. That would be a great thing to do.
Hello, Houston. The Endeavour is on station with cargo, and what a fantastic sight.
Beautiful news. Romantic, isn't it?
Oh, this is really profound. I'll tell you. It's fantastic.
At the high level, it makes sense that an aerospace engineer is designing a satellite, but like when we get down to it, and all the pieces that need to work together, tens of thousands of miles, if you will, that's what's the orbit?
About 600 kilometers.
600 kilometers. Okay, so to do that 600 kilometers away requires incredible skill. So can you say a little bit about, this is, I think, the work of yourself and your students. Yeah. Can you say a little bit about the kinds of students that might make their way to your lab?
And I'll say that we rely heavily on the talented students that we've got here at Tech to do all of this work, because these missions are very complex. So at any one time, and I'll throw out that at Georgia Tech in the aerospace program, we have 6 active satellites in development right now. Mm-hmm. And so I'm principal investigator for 3 of them. Range is just one of them. There's colleagues within the Space Systems Design Lab and at Aerospace. They manage some others. So we have 6 missions currently in development at different stages. Some are going to launch soon. Some are going to launch in a couple years from now. And each one of these has upwards of 10 to 20 plus undergraduate and graduate students working on them. And they have the whole skill spectrum, because you need someone who is knowledgeable in programming. You need circuit board design. You need CAD. You need structural design. You need to understand thermal properties. We have lots of mechanisms. So we have mechanical engineers, and we have computer scientists, and we have electrical engineers. We have a whole team, and I recruit from across the campus. Yes, there are certainly aerospace engineers, because we need them to do the orbit analysis and the mission design, but we need everybody, because if you think about what the mission encompasses, it's everything from design to electronics to programming to science analysis. Ultimately, we want to do some analysis after the mission launches. There's radio signals that we need to interpret. That's how we communicate with the satellite. So the full spectrum of skill sets need to go into these missions.
Okay, loud and clear, Dave, and your go for liftoff. And I assume you've taken your Explorer hats off and put on your pilot hats.
It seems like we maybe have a mini NASA here at Georgia Tech. Can you talk about, could somebody come to Georgia Tech and kind of do the whole thing as if you think that only NASA could do?
Yes, in many ways, I would say. We have the capability here, and I think we're fairly unique, or just one of a handful of universities that could even offer this. We have the ability to handle every single phase of a small satellite mission. This includes the mission design, so the early concept work, to the fabrication of it. So at Georgia Tech's Aerospace, we have a fantastic machine shop within the SSDL, the Space Systems Design Lab. Amongst the shared facilities that we have of all the professors there, we have thermal vacuum chambers, we have vibration tables that are we use out at Georgia Tech Research Institute. So we can do all of the testing and analysis. We have the setups to do hardware in the loop testing. where we're evaluating attitude control systems and the communication systems. We have multiple ground stations. We have an S-band station. We have multiple what are UHF radio stations, and those we use during mission operations.
Mm-hmm.
So after the satellites launch, we can download the data here. All of our mission control is here at Georgia Tech. So we don't delegate any of that other than the actual launch itself to any other party. And so that's a pretty unique feature. And the number of satellite missions that we have in the works, like I mentioned, we have 6 active flight projects in the works, enables a student, if they have the interest, if they want to go beyond just what they learn in the classroom, the opportunity is there to come to Georgia Tech and actually get involved in a mission that is going to launch in space. And that's a pretty...
Wow.
I certainly didn't have that when I was an undergraduate, so I feel I enjoy that we have that opportunity here at Georgia Tech, and the students really enjoy it too. They love the challenge of it. They love the knowing that what they're working on is going to go into space.
Apollo 15, Houston, over.
Hello, Houston. Endeavor's on the way home with a burn status report for you.
Roger, sounds good. Standing by.
One of the questions we always ask is what makes you an uncommon engineer? Because I think, a lot of the things that you talked about, I don't think people necessarily think about as engineers. But so, Brian, what makes you an uncommon engineer?
So I would say I'm uncommon in the sense that I'm as excited as much by the science and the discovery behind some of these space missions that we work on as about the process of building the systems and the satellites that are required to achieve those goals. So I think many engineers are very content to just work on a particular subsystem, whether it's an attitude control or a propulsion system or a power system, flight software, what have you. But those people tend to be relatively disconnected with the larger objective of the mission. And so I'm fortunate to have this opportunity to work on all aspects of a satellite mission. So all of these satellite missions that I've talked about, the range mission, the target mission, we have taken those from a mission concept, so from a PowerPoint presentation, all the way to gathering data from an orbiting satellite and actually executing that. So we get the full spectrum from fabrication to testing to the analysis and interpretation. And so I'm just as excited by the science return and the data that we're going to get back by these missions as I am in the engineering processes. So in this sense, I think I'm a little bit uncommon from most engineers in that I'm a true I love the science and the engineering. I like how they interact.
Well, we're really lucky to have you here today to talk about your project, but I think just as much really lucky to have you here at Georgia Tech because that kind of expertise, that kind of interest really benefits so many students, and we just really want to thank you for today and for everything you're doing at Georgia Tech. So thanks so much, Brian. We appreciate it.
Thank you.
Next time on The Uncommon Engineer, we'll meet Dr. Annabelle Singer and her work on memory, cognition, and possible therapies for Alzheimer's disease.
Apollo 15, this is recovery, over. Apollo 15, everybody's in good shape.
We had a lot of support from a lot of people, and I'd just like to say that we appreciate every bit of it, and we could not have done the mission. We couldn't have gone one step without the support of the many, many thousands of people involved. Thank you very much.